You want to believe we'll hear from aliens someday? Fine. But let me tell you something that should bother you, really bother you, if you think about it honestly. Every signal traveling through space is a message from a dead civilization. Not maybe dead, not probably dead. By the time any radio wave, any laser pulse, any whisper of intelligence crosses the galaxy and reaches our antenna, the beings who sent it are gone. Thousands of years gone. Maybe millions. So here's the question nobody in the search for extraterrestrial life wants to sit with. What exactly are we listening for? A ghost. We are building billion-dollar telescopes to listen to ghosts, and I think that's the most fascinating thing I've ever heard in my life. Stay with me, because once you understand why that's true, the universe gets a lot stranger and a lot more honest. Let's start with something simple. Something you already know but haven't fully sat with. Light travels at 299,792,458 meters per second. That's not an approximation. That's the number. It's exact because we've actually defined the meter in terms of how far light travels in a fraction of a second. We're that confident in it. In the history of science, very few numbers have earned that kind of trust. The speed of light has. Now, the nearest star to our sun is called Proxima Centauri. It sits about 4.24 light years away. That means the light leaving that star right now, this instant, as you watch this, will take 4 years and 3 months to reach your eye. When you look at Proxima Centauri in the night sky, you are not seeing it as it is. You are seeing it as it was in the year 2021. That's not a metaphor. That's physics. The photon hitting your retina left that star before this video existed. Now push that further. Most of the stars you can see with your naked eye on a clear night, the ones people have named and written poems about for thousands of years, are between 100 and 1,000 light years away. The light you're seeing from them left before Columbus sailed, before the Black Death, before the printing press. Some of it left before Islam, before Christianity, before Rome. You look up at a clear sky, and you are not seeing the universe. You are reading an ancient newspaper, and the further you look, the older the edition. This is not a minor footnote to astronomy. It is the central fact of astronomy. Everything we know about the cosmos, we know from old light. Old light. And when it comes to the question of alien civilizations, this fact doesn't just complicate the picture. It changes the entire conversation. Here's where it gets specific. The Milky Way galaxy is roughly 100,000 light years across. Our civilization, meaning the point at which we started broadcasting detectable electromagnetic signals into space, is about 100 years old. We sent our first strong radio signals into the cosmos around the 1920s. Those signals are now 100 light years out, expanding in a sphere from Earth. That sphere contains roughly 15,000 star systems, out of about 300 billion in the galaxy. We have announced ourselves to 0.000005% of the Milky Way. We are a candle in a continent-sized room, and we lit the candle 5 seconds ago. Now flip the math. If there's a civilization 1,000 light years away, and they sent us a signal today, we'd receive it in the year 3026. If they sent it 1,000 years ago, we receive it now. But that signal describes a civilization from the year 1025, the year when most of Europe couldn't read, when the Aztec Empire didn't yet exist, when no one on Earth had any concept of radio waves, telescopes, or the galaxy we live in. That's who we'd be hearing from. Not the civilization as it is. The civilization as it was, when it was barely getting started, or perhaps winding down, or perhaps already gone. And here is the thing that keeps coming back to me whenever I think hard about this. We have no way to know the difference. The signal arrives. It's real. It's intelligent. The math checks out. We've detected it and verified it, and we're sure. And at that moment, the civilization that sent it is, with near certainty, no longer what it was when it sent the signal. It may be vastly more advanced. It may be extinct. It may have changed so completely that the beings who sent that signal would not recognize their own descendants. We don't know. We can't know. Because the speed of light is the only courier the universe provides, and that courier always delivers late. Think about what this means for the famous question, are we alone? Suppose the answer is no. Suppose the galaxy is full of civilizations, hundreds of them, broadcasting away. The signals are out there, they're real. But every single one of them is a snapshot from the past. Every one is a letter that was written, sealed, put in a bottle, and thrown into an ocean that takes thousands of years to cross. By the time the bottle washes up, the person who wrote the letter is long dead, Their children are dead. Their nation may not exist. The language they wrote in may be extinct. We would not be making contact. We would be doing archaeology at the speed of light. Now, some people hear this and they think, well, fine, so we can't have a real-time conversation. But we could still learn something, right? We could confirm they exist. That would matter. And yes, it would matter enormously. Just knowing we weren't alone in the universe would be one of the most significant realizations in human history. I don't dismiss that, but I want to push past the comfort of that answer because there's something harder underneath it, and it's worth looking at directly. The hardest version of this problem has a name. You've probably heard it. It's called the Fermi Paradox, and it's named for Enrico Fermi, the physicist who built the first nuclear reactor and who, during a lunch conversation in 1950 at Los Alamos, asked a question so simple it felt almost rude. The galaxy is old. It's been here for 13 billion years. Stars with planets have existed for nearly that long. If even a small fraction of those planets developed life, and if even a small fraction of that life became intelligent, and if even a small fraction of that intelligence became technological, we should, by any reasonable calculation, have heard something by now. The galaxy should be buzzing, but it isn't. It's quiet. Where is everybody? That was Fermi's question. And in the 70-plus years since he asked it, nobody has answered it, not definitively. We have hypotheses. We have Fermi's own guess, which was that interstellar travel and communication might be fundamentally harder than we imagine. We have the great filter idea, the notion that somewhere between simple chemistry and spacefaring civilization, something kills most lineages off. Something hard. Something almost universally fatal. We don't know what. Maybe it's the transition from single-celled to multicellular life. Maybe it's the development of nuclear weapons before the wisdom to use them carefully. Maybe it's something we haven't thought of yet. But the silence of the galaxy is real, and it demands explanation. Here is one explanation that doesn't get discussed enough: the delay problem. Even if the galaxy were full of civilizations at various stages of development, the ones close enough to us for their signals to have arrived yet might represent only the very earliest and the very weakest signals those civilizations ever produced. Think about our own trajectory. We've been broadcasting radio waves for 100 years. In the first few decades, those signals were weak and scattered. The kind of TV and radio broadcasts that leaked off into space from the mid-20th century are already so diffuse and noise-drowned that they'd be nearly undetectable from even 1 or 2 light years away. They fade fast, so the window in which a civilization like ours is accidentally visible to the cosmos is narrow. And the signals from that window look nothing like a civilization at its height. They look like static with a pattern, easy to miss. Which means that even if we detected something, the civilization that sent it was probably broadcasting unintentionally in their early days when they were young and loud and leaky, their golden age, their full technological maturity that comes later, and later they might have stopped broadcasting entirely by the time they figured out tightly focused laser communication or quantum entanglement channels or whatever comes after radio. They stopped spraying noise into space. They got efficient. They went quiet. And from our vantage point, they vanished. This is not a comforting thought. It means the cosmos might be older and more advanced and more silent than we can imagine, and the silence isn't evidence of emptiness. It might be evidence of maturity. There's a physicist named Frank Drake who in 1961 developed an equation, the Drake equation, to estimate how many communicating civilizations might exist in our galaxy at any given moment. It's not a computational tool exactly. It's more like a framework for organizing your ignorance. It breaks the big question down into smaller questions. How often do stars form? How many have planets? How many of those planets could support life? How many actually develop life? How many of those develop intelligence? How many of those communicate? And how long do they communicate before going silent or going extinct? Multiply all those terms together and you get an estimate. The problem is we don't know most of those values. We're guessing, informed guessing, based on what biology and planetary science have taught us, but guessing. The most uncertain term in the whole equation is the last one, the average length of time a civilization remains detectable. Drake called it L, and L turns out to be the term that matters most. If civilizations broadcast for 1 million years on average, the galaxy should be loud. If they broadcast for only a few centuries before going silent by accident or advancement or extinction, the galaxy goes quiet almost immediately. And our observations suggest quiet, We have been scanning the sky since 1960. That was the first serious search run by Frank Drake himself, a project called OSMA, pointing a radio telescope at two nearby sun-like stars for about 150 hours, listening for anything that sounded intelligent. He heard nothing useful. In the decades since, we have searched millions of frequencies, pointed at thousands of targets, and built increasingly sensitive instruments. The most sustained effort, the SETI Institute and its associated programs, has produced decades of data. In all of that, across all of those frequencies, all of those years, all of those targets, we have found exactly one signal worth talking about. It was detected on August 15, 1977, by astronomer Jerry Ayman at the Big Ear Radio Telescope in Ohio. It lasted 72 seconds, exactly the length of time the telescope's field of view would sweep across a fixed point in space. Ayman circled it on the printout and wrote one word in red pen in the margin. Wow! The signal has been called the wow signal ever since. It was powerful. It was narrowband, meaning it occupied a very precise frequency rather than a broad smear of noise, which is a signature of something artificial rather than natural. It came from the direction of the constellation Sagittarius, and it has never been detected again, despite numerous follow-up attempts over the subsequent 4 decades. We don't know what it was. Could have been an alien broadcast. Could have been a natural phenomenon we haven't identified. Could have been interference from a source closer to home. We genuinely don't know. What we do know is that we got one 72-second blip in 60-plus years of searching, and then silence. Whatever it was, it didn't repeat. Or if it repeated, we haven't been looking in the right place at the right time. Think about what that means from the delay perspective. If the WOW signal was sent by an intelligent civilization, let's say they're 1,000 light-years away, somewhere in the direction of Sagittarius, then they sent that signal in the year 977, 1,000 years ago. The signal crossed 1,000 light-years of empty space and hit our telescope for 72 seconds on a summer morning in Ohio, and we weren't even certain what we had. And the civilization that sent it has had 1,000 years of additional history since then, moving in some direction we cannot know, possibly thriving, possibly gone. We sent no reply. Not immediately. It took years before we agreed it was worth attempting a response, and by the time any response we sent reaches where the signal came from, it will be the year 3977. 3,000 years from now. Whatever is there will receive a message from us. A species that used radio waves in the early 21st century before we even knew how to leave our own solar system. They'll be reading about cavemen. This is the conversation we're trying to have. Not a phone call. Not even a letter chain. A message in a bottle thrown into an ocean that takes 1,000 years to cross, with a return address and no certainty that anyone is still at home. And yet, and here I have to be honest with you about something, the fact that this conversation is so hard, so delayed, so fundamentally limited, that doesn't make it less remarkable. It makes it more remarkable, because despite all of this, we are still searching. We are still building instruments. We are still pointing them at the sky, not because we expect a real-time dialogue, but because even a confirmed ghost, even a signal that proves something lived out there, once 1,000 years ago or 10,000, would change everything. It would tell us we are not a fluke. It would tell us that chemistry and physics and evolution don't only produce intelligence once, in one lonely corner of one ordinary galaxy. It would tell us that the universe is, at some level, set up for this, and that changes how you think about our own situation. Not in some vague philosophical way, in a specific, concrete, unsettling way. Here is where Feynman's reality check actually bites. Not in the astronomy. In the mirror, it holds up. If we detect a signal tomorrow from a civilization 500 light-years away, a civilization that existed in the year 1526, we face an immediate question. We can't ask them how they survived. We can't ask what they learned. We can't ask if they made it through whatever the great filter is, or whether they saw it coming, or whether they just got lucky. We can't ask anything. We receive, we study, we wonder. That's it. But the question turns around. Right now, today, a civilization 500 light-years away, with technology better than ours, might be receiving our signals. The signals we sent 500 years ago. They're watching us in the year 1526. They're seeing the very beginning of the scientific revolution. They can see that we had gunpowder and ships and a printing press. They can see that we were about to figure things out. And from their vantage point, the question is the same one we'd ask about them. Did they make it? Did those beings with the new printing presses and the sailing ships and the gunpowder figure out how to not destroy themselves? Did they survive long enough to hear back from us? We don't know if they survived. They don't know if we survived. Neither of us can know, because the speed of light is fixed, and the distance is vast, and time moves only in one direction. So the Fermi Paradox isn't just a puzzle about alien silence. It's a puzzle about civilizational survival. And the answer to the question of where everyone is might be the same as the answer to the question of how long any intelligent species tends to last. Those two questions, why is the galaxy quiet and how long do we have, might be the same question. One question wearing two faces. Now I want to bring in a concept that sometimes floats around these conversations and often gets used loosely, and I want to be precise about it because it matters here. The concept is called the observable universe. The observable universe is not the whole universe. It's just the part we can in principle see. It has a radius of about 46 billion light years, not 14 billion. You might expect 14 billion since the universe is about 13.8 billion years old, and light travels at 1 light year per year. But the universe has been expanding the whole time, so the most distant light we can detect today actually originated from matter that is now 46 billion light years away, because that matter has been carried outward by the expansion of space itself. This is important, because it means there is almost certainly a universe beyond our observable bubble, a region from which no light has ever reached us, and never will, because the universe is expanding faster than light can cross the distance. Those regions, if they exist, and the math strongly suggests they do, are causally disconnected from us. Whatever happens there, whatever intelligence might live there, we will never know. Not because of insufficient technology, not because of budget constraints, because physics forbids it. The universe is in this sense larger than knowable, and we live in a small, bounded, time-limited window of it. The cosmic address is humbling. We're in the Orion arm of the Milky Way, a barred spiral galaxy, part of the local group of galaxies, itself a part of the Virgo supercluster, itself a tiny node in the cosmic web of filaments and voids. We sit in a bubble of observable space 92 billion light-years across, and within that bubble, we have managed to search, in any meaningful way, a volume roughly equivalent to a grain of sand compared to all the beaches on Earth. When people say we've been looking and haven't found anything, yes, that's true. It's also true that we've barely started. The search is young, the instruments are new, the methods are primitive compared to what will exist in 100 years or 1,000. It would be extraordinary hubris to conclude from 6 decades of radio scanning that the galaxy is empty, but it would be equally extraordinary wishful thinking to assume it's full just because we want it to be. Feynman had a phrase he used when he wanted to be honest about where knowledge ended. He'd say, "I don't know," and then he'd say, "and that's interesting, not devastating." Interesting, because not knowing is where the real questions live. Not knowing is where science starts. We don't know if we're alone. We don't know if the wow signal was intelligent. We don't know what the great filter is, or whether it's ahead of us or behind us. We don't know how long civilizations typically last. We don't know if communication across interstellar distances is even a thing intelligent species do long-term, or whether it's just a brief, early-stage behavior, the cosmic equivalent of a toddler banging pots together, loud and temporary. What we do know is physics. We know the speed of light, we know the size of the galaxy, we know the delay, and those facts taken together tell us something important. Contact, as we imagine it, mutual, real-time, conversational, is almost certainly not how this works. The universe is not set up for that. It's set up for long silences and ancient whispers and records that arrive after the civilization has moved on or gone dark. If we ever detect something, the moment will be extraordinary. The detection itself, the proof of existence, that will matter more than we can probably express right now. But the response will be a 1,000-year conversation at best. A message sent to a past. A letter written across an interval of time so large that the species doing the writing and the species doing the reading might share almost nothing except the physics that governs them both. That's the reality check. Not that the search is wrong, not that it's hopeless, but that the version of contact we carry in our heads, the version from movies, from stories, from the deep human wish not to be alone, that version is incompatible with what we know about space and time and light. The real version is stranger, it's slower, it's sadder in some ways, and in other ways it's more interesting, because it forces you to think about what we're actually trying to accomplish out here, and what it would mean, and how long it takes. Here is the thing about ghosts, though. A ghost is evidence that something was there, and something was there once, alive and burning and perhaps broadcasting, is not nothing. It is the opposite of nothing. It is the most important discovery we could make, not that we have a neighbor we can call, but that the universe produces minds, that intelligence is not a one-time accident on a wet rock near an ordinary star, that in the vastness and silence and darkness, something else, somewhere else, once looked up, even if we never get a reply, even if every signal we ever detect turns out to be a memory, a fossil of transmission, an echo from something that burned bright and went dark 1,000 years before we were ready to listen, it would still matter. It would matter in the deepest way a scientific discovery can matter. It would tell us what kind of universe this is. Right now, we don't know what kind of universe this is. We have one data point, us, one civilization, one planet, one improbable chain of events that produced beings who can ask the question. That's not enough to generalize from. It's not enough to say this happens often, or rarely, or somewhere in between, to say anything about the universe. You need more than one example. You need a second. We've been looking for 60 years. We're going to keep looking. And in the meantime, every day that passes without a signal tells us something too. It narrows the space of answers. It makes some explanations less likely, and others more. The silence is data, uncomfortable data, but honest data. And honest data, even when it's uncomfortable, is always better than a comforting story. The speed of light is not going to change. The distances are not going to shrink. The delay is permanent and irreducible. And yet right now, at this moment, there might be a signal crossing the space between us and something else, carrying information about a civilization that may be long gone, crossing a distance so vast that the light left before human beings had writing. It's moving at 299,792,458 meters per second, never stopping, never slowing, crossing the dark between the stars, and it may reach us next year, or in 1,000 years, or it may miss us entirely, but it's out there, maybe, and the fact that we can ask that seriously, not as science fiction, not as fantasy, but as a genuine scientific question with instruments and frequencies and data and funding, that is new. In the history of our species, the ability to seriously look for answers to this question is almost brand new. We are, cosmically speaking, just old enough to start asking, just barely old enough to listen. Whatever we find or don't find, we will have to sit with the delay, with the fact that the universe moves on its own schedule and not ours, with the fact that any message we receive is already ancient by the time it arrives, with the fact that we exist in this particular century, on this particular planet, in this brief window, when we're loud enough to be detected and curious enough to look, and we don't know if that window is the beginning of a long story or somewhere near the end of a short one. That's the question you're left with. Not whether we're alone, not whether the signal is out there, but whether we're early or late, whether we're one of the first civilizations to reach this point or one of the last, whether the silence means the galaxy is still waiting for something to rise, or whether it means almost everything that was going to rise already has and already went quiet, and we are the straggler, arriving after the party, finding empty bottles and a note that says, "We were here, we tried to reach you, we ran out of time." The Milky Way is 100,000 light years across. We've been broadcasting for 100 years. We have told a circle of space 100 light years wide that we exist. That circle is expanding at the speed of light, 1 light year per year, in all directions. And somewhere out there, if someone is listening, if they have instruments sensitive enough and pointed in the right direction at the right moment, they will hear us. They'll hear our old radio dramas and weather reports and military radar pulses. They'll hear the accidental noise of a species just waking up. And by the time they hear it, we will have been awake a very long time. Whether we're still here when they answer, that's not a physics question. That's our question, the one we have to answer ourselves in real time, with no delay.